It is generally not recommended to attach sidewalks directly to a house at the meter or service location. This can create a tripping hazard if the sidewalk settles unevenly. Grounding requirements for houses vary by location and the applicable electrical code. However, it is generally required to have a grounding electrode system that includes at least 2 ground rods driven into the earth. In some cases, the water pipe can also be used as part of the grounding electrode system. Whether or not it is a violation to have a sidewalk attached to the house at the meter location depends on local building codes. In some areas, it may be allowed, while in others, it may be prohibited. While the water pipe can be used as part of the grounding electrode system, it is not recommended as the sole grounding source. Water pipes can corrode over time, which can affect their conductivity. Additionally, the water pipe may not be accessible for grounding if needed. If it is not possible to drive ground rods through the sidewalk, alternative grounding methods can be considered. Firstly, concrete encased electrodes. These electrodes are embedded in concrete and provide grounding protection. Secondly, ground rings. Ground rings are a series of connected electrodes that are buried underground to create a grounding system. Thirdly, grounding plates. Grounding plates are metal plates that are buried underground and used for grounding. If drilling through the sidewalk is necessary, use a hammer drill with a carbide-tipped bit. Start with a small bit and gradually increase the size until the hole is large enough for the ground rod or grounding plate. Use a sledgehammer or post driver to pound the ground rod into the earth. Ensure that the rod is driven deep enough to provide a good electrical connection. Grounding electrodes need to be in contact with moist soil to function properly. If the soil is dry, it may be necessary to add water or use a soil amendment to increase moisture levels. When dealing with electrical grounding systems, there are several key concepts and requirements outlined in the National Electrical Code, particularly Article 250, that one should be aware of. These include the purpose of grounding electrode systems, bonding, and specific rules for different types of systems. The purpose of grounding is primarily to provide a low impedance path for fault current to return to the source. This helps to ensure that overcurrent protective devices, such as circuit breakers or fuses, operate quickly to clear the fault. Grounding also helps to limit voltage on equipment enclosures and other conductive parts, reducing the risk of electric shock. A grounding electrode system typically consists of one or more grounding electrodes that are bonded together to form a single grounding system. Acceptable grounding electrodes include metal underground water pipes, concrete encased electrodes, ground rings, rod and pipe electrodes, and plate electrodes. The code specifies requirements for the size, material, and insulation of these electrodes. For example, if using ground rods, the code requires at least 2 ground rods to be installed and spaced at least 6 feet apart. The rods must be at least 8 feet long and made of approved materials such as copper or galvanized steel. Concrete encased electrodes, also known as UFA grounds, must consist of at least 20 feet of bare copper conductor encased in concrete that is in direct contact with the earth. Ground rings must be buried at least 30 inches below the surface of the earth and must encircle the building or structure. Bonding is the process of connecting all non-current carrying metal parts of an electrical system together to create a low impedance path for fault current. This includes bonding equipment enclosures, metal raceways, and other conductive parts. Bonding helps to ensure that all metal parts are at the same electrical potential, reducing the risk of electric shock. The main bonding jumper is used to connect the equipment grounding conductor to the grounded conductor at the service equipment. The size of the main bonding jumper is based on the size of the service entrance conductors. Different types of electrical systems, such as alternating current and direct current systems, have different grounding requirements. For example, alternating current systems are typically grounded at the service equipment, while direct current systems may be grounded or ungrounded, depending on the application. Article 250.50 covers the grounding electrode system and requires that all available electrodes be bonded together to form the grounding electrode system. This includes metal underground water pipes, concrete encased electrodes, and ground rings. Article 250.52 specifies the requirements for grounding electrodes, including the size, material, and installation requirements. Article 250.53 provides additional requirements for ground rods and pipe electrodes, including the depth and spacing requirements. Article 250.66 covers the size of the grounding electrode conductor, which is used to connect the grounding electrode to the service equipment. The size of the grounding electrode conductor is based on the size of the service entrance conductors. Article 250.104 covers the bonding of metal water piping systems and other metal piping systems. This article requires that metal water piping systems be bonded to the grounding electrode system to ensure that they are at the same electrical potential. When installing a grounding electrode system, it is important to follow all applicable codes and standards. This includes ensuring that the grounding electrodes are properly sized and installed, and that all bonding connections are made correctly. It is also important to inspect the grounding electrode system regularly to ensure that it is in good condition and that all connections are tight. In cases where it is difficult to drive ground rods due to soil conditions or obstructions, alternative grounding methods may be used. These include using concrete encased electrodes, ground rings, or chemical ground rods. Chemical ground rods are filled with chemicals that help to improve the conductivity of the soil, making them more effective than traditional ground rods in certain situations. When using alternative grounding methods, it is important to follow the manufacturer's instructions and to ensure that the grounding system meets all applicable code requirements. It is also important to consider the long-term maintenance requirements of the grounding system. For example, chemical ground rods may need to be replaced periodically, depending on the soil conditions and the type of chemicals used. Grounding is a critical aspect of electrical safety, and it is important to understand the principles and requirements of grounding to ensure that electrical systems are installed and maintained safely. By following the code and using best practices, it is possible to create a safe and reliable grounding system that will protect people and property from electrical hazards. When dealing with situations where sidewalks or other obstructions prevent the installation of traditional ground rods, careful consideration must be given to alternative grounding methods to ensure compliance with electrical codes and maintain safety. If sidewalks are attached directly to the house at the meter or surface location, this can present unique challenges for grounding. The primary issue is how to effectively install a grounding electrode system when the soil around the foundation is covered by concrete. The National Electrical Code provides guidelines and options for such situations, but local codes may also have specific requirements that must be followed. The NEC generally requires a grounding electrode system consisting of multiple electrodes to ensure a reliable, low-impedance path to ground. Common electrodes include ground rods, ground plates, underground metal water pipes, and concrete encased electrodes. When sidewalks or other obstructions are present, installing traditional ground rods becomes difficult or impossible. In such cases, alternative grounding methods must be considered. One option is to use concrete encased electrodes, often referred to as U-for-ground. This involves encasing a length of bare copper conductor within the concrete foundation of the building. The NEC specifies the requirements for U-for-grounds, including the minimum length of the conductor and the amount of concrete coverage. If the existing foundation does not have a U-for-ground, it may be necessary to create one by encasing a conductor in a new concrete structure, such as a footing or pad. Another alternative is to use ground rings. A ground ring is a continuous loop of bare copper conductor buried in the earth around the perimeter of the building. The NEC specifies the requirements for ground rings, including the minimum size of the conductor and the depth at which it must be buried. Ground rings can be a good option when it is not possible to install ground rods due to obstructions, but they require more excavation than other methods. If ground rods must be used, one approach is to drive them as close to the building as possible, avoiding the sidewalk. This may require driving the rods at an angle to clear the obstruction. The NEC specifies the minimum depth at which ground rods must be driven, and it is important to ensure that the rods are in contact with the earth along their entire length. If it is necessary to penetrate the sidewalk to install ground rods, special tools and techniques may be required. A hammer drill with a carbide tip bit can be used to create a hole through the concrete. The hole should be large enough to accommodate the ground rod without damaging the concrete. Once the hole has been drilled, the ground rod can be driven into the earth using a ground rod driver or a sledgehammer. It is important to avoid damaging the sidewalk during the installation process. After the ground rods have been installed, they must be connected to the grounding electrode system using a grounding electrode conductor. The grounding electrode conductor must be sized according to the NEC and must be securely connected to the ground rods and the service equipment. In some cases, the metal water pipe entering the building may be used as a grounding electrode. However, the NEC requires that the water pipe be supplemented by another electrode, such as a ground rod or a U for ground. The water pipe must also be bonded to the grounding electrode system to ensure that it is at the same electrical potential as other grounded components. When dealing with sidewalks attached to the house, it is important to consider the potential for settling or movement. If the sidewalk is not properly supported, it may settle over time, which could damage the grounding electrodes or the grounding electrode conductor. In such cases, it may be necessary to provide additional support for the sidewalk or to use flexible grounding connections that can accommodate movement. It is also important to consider the potential for corrosion when installing grounding electrodes in concrete or soil. Concrete can be corrosive to some metals, and soil can contain chemicals that can accelerate corrosion. To prevent corrosion, it is important to use grounding electrodes and conductors that are made of corrosion-resistant materials, such as copper or stainless steel. It is also important to protect the grounding connections from moisture and other contaminants. In summary, grounding electrode systems require at least 2 electrodes, and if it is difficult to drive ground rods through sidewalks, alternative grounding methods can be considered. Concrete-encased electrodes are embedded in concrete and provide grounding protection. Ground rings are a series of connected electrodes that are buried underground to create a grounding system, and grounding plates are metal plates that are buried underground and used for grounding. If drilling through the sidewalk is necessary, use a hammer drill with a carbide tip bit, starting with a small bit and gradually increasing the size until the hole is large enough for the ground rod or grounding plate. Use a sledgehammer or post driver to pound the ground rod into the earth, ensuring that the rod is driven deep enough to provide a good electrical connection. Grounding electrodes need to be in contact with moist soil to function properly, and if the soil is dry, it may be necessary to add water or use a soil amendment to increase moisture levels. Understanding the NEC and consulting with a qualified electrician can help ensure a safe and compliant electrical system.